Okay, this is the lesson video over section 12.2 for multivariable calculus. And in this section, we're just going to talk about really just basic vector operations. And this should be material that is review to all of you. So the reason we're going to spend an entire class just working on the basics of vectors is really, there's two reasons for it. Number one, this is going to be very, very important to us throughout the entire year. And number two, even though you've seen it before, for most of you working with vectors, especially vectors in 3D, you probably haven't done that in quite some time. Some of you, it might have been 2 years since you were in pre-calculus. Some of you, it might have been 3 years. So I know there's one person who took BC calculus as a sophomore and has not taken calculus since then. So that gives you a lot of time in between working with the vector operations and now. So it may be that you've seen it in physics a little bit, but it's really kind of hit and miss in terms of what you've seen and what you haven't seen since pre-calculus. So with that said, I'm going to go through some of the absolute basics of vectors, and there's not really a lot to this. I'm going to go through this pretty fast. The biggest thing that I want you to focus on more than anything else is the notation and the way that we're going to draw these in 3D. And drawing them in 3D might be something you don't have a lot of practice with. That's something we'll focus on a little bit more in this class. Okay, so we've got in here in the basics of vectors, just some kind of basic knowledge and basic vocabulary that we're going to use. So when we are talking about a vector, you can see we've got some different notations that we're going to use. And when you look in your textbook, you're going to see this a lot, where they're going to indicate that's the vector v. Well, they're going to indicate it with bolded letters. When you're writing a vector, it's going to be very difficult for you to write bolded letters. So I would recommend you use different vector notation. So if I were going to write the vector v, I usually write it like this. So the v and then like a half arrow on top of that v, or you might see it written like this with an arrow on top. And then in the end, eventually we'll get to the point where we're going to have vectors in component form. And when we start seeing vectors in component form, a lot of times we'll show component form like this, where we'll have, if it's a two-dimensional vector, we might have like the number 2, 3 here. That would be 2 units in the horizontal direction, 3 units in the vertical direction. And then if it was a 3-dimensional vector, kind of the similar notation. When you see those angled brackets, that's indicating vector notation. Okay, so we've got the idea here of a displacement vector. So keep in mind, when we talk about a vector is an object, I guess we could call it, that has a direction and a magnitude. So when I talk about a displacement vector, I'm not just talking about, where did I finish and where did I end up? What I'm really looking at is the direction that I traveled and how far away was it. So those are the two things that a displacement vector can get me. When we talk about the initial point, so if we were thinking about that in terms of like a displacement, if you look at this vector AB that's up here, you can see that I've got this point A would be my initial point, and then the point B over here would be my terminal point. And when we say we have equivalent vectors, if you look at vectors v and vector u, or you could call it vector AB and vector CD, if you look at those two vectors, those would be considered to be equivalent vectors. They have the same magnitude and they have the same direction. Notice that point A and point C are not in the same place, but in terms of where does the vector start versus where does it end, that has the same quantities from a displacement standpoint, and from a direction standpoint, we're going to get, the same magnitude and the same direction. Okay, so when we combine vectors, really what we're talking about here primarily is just vector addition. So when you combine them, you're just going to add the corresponding components. And when I talk about the vector components, we're talking about, in 2D, we'd be talking about like an I component and a J component, but we would just add those corresponding components together. When we do it graphically, we're going to line the vectors up from head to tail. So you can see here we've got two vectors, u and v, And if we were going to find the sum of these vectors, we've got u plus v. They're lined up head to tail. And then the resulting vector is going to use the initial point, and it's going to point to the terminal point. That would be the vector u plus v. But in terms of the actual math that we do, to the calculations that we do to get the vector u plus v, all we're going to do is add corresponding components. And you can see over here, it doesn't matter which way I set that up, which one I use as the initial vector. I'm going to get the same result either way. Okay, we also have what's called scalar multiplication. And scalar multiplication just means that I'm going to multiply my entire vector by some scalar value. So you can see, for example, here, I've got this vector v. If I do the vector 2v, it's going to have the same direction, but now my vector is going to have twice the length. So if we had that in component form, each of the components would be multiplied by 2. You can see the same thing with 1/2 v. We can also multiply by a negative scalar. So keep in mind, if we make a vector negative, what we're doing is reversing the direction of that vector. Okay, so here's where we start to get into the components of the vectors. So this is the component form that I was talking about earlier. And we've got this vector A that is going between A and B. So from A to B, if I want to find the components, I'm going to do x2 minus x1, y2 minus y1. If it was 2D, that would be the end of it. But then in 3D, we're also going to do z2 minus z1. So typically we refer to this as the I component. This we call the J component, and this one we call the K component. So we don't have to write I, J, and K when we have it in that bracketed component form, because it's just assumed that the first component is the I, the second is the J, and the third is the K. When we're finding the length of a vector, remember, all we're doing is finding the hypotenuse of a triangle. We create a right triangle just by using the pieces that were given, the components that were given, and then we just find the square root of the sum of the squares of those components, and that will give us the magnitude of the vector. So not really that difficult to do. If you think about your distance formula, that's really what we're doing. Here are some general properties of vectors. Adding vectors, adding 0 to a vector, multiplying by a scalar. Notice that this one here, we're multiplying by the scalar CD. So we can multiply D to the vector A and then leave the C out, or we can multiply the C through. Also notice here, we've got the associative property like you've seen before. It doesn't matter how I group the vectors together. If I add the 3 vectors, it's still going to give me the same result. So all common properties that you've seen before. Here are what we call the standard basis vectors. So I talked about the I component, the J component, and the K component. Those are called the basis vectors. And again, I'm typically going to write them like this, I, J, and K. But again, in your book, you're going to see, this bolded notation. But those are the vectors that have a length of 1 that point essentially in the 3 directions. If you want to think of it as like the X, the Y, and the Z direction. The I direction is the horizontal direction. That would be along the X-axis. The J is along the Y-axis, and then the K would be along the Z-axis. So each of those is a vector with a length of 1 that points in the same direction as the X, Y, or the Z-axis. Okay, so let's take a look at this next one. It says, find the components of vector V of length root 5 that extends along the line through A and B. So what I want you to do is just take a minute and try to work through this problem, and then I'll show you the solution. So you can pause the video, and then I'll put the solution up here in just a second. Okay, so here's what you should have ended up with. Notice that the vector AB, I found the difference in the X's, the difference in the Y's, and the difference in the Z's, and that's where I came up with this result. I can write it like that, or I can write it in this form. It doesn't really make a difference. It's really a matter of preference. I'm usually going to use this bracketed form because it's a little bit less writing. That doesn't mean you have to do it that way. It doesn't mean that your answers aren't going to be required to be written this way. You can see any of the forms. So the main thing is when you're given the option to write the vectors however you want to write them, it's totally up to you, but make sure you know how to read all the notations. Okay, so the next thing I did here was I figured out, okay, what's the magnitude of this vector? That's what this notation means. When we take the absolute value, that's always measuring the distance. So we're saying what's the distance or what's the length of the vector? Well, the length of this vector is the square root of 45. Notice that we want the length of the vector to be square root of 5. So what I'm going to do here, and this is what I've done right here, is I'm going to create a unit vector. And when we say unit vector, remember that means a vector with a length of 1 that points in the same direction as your vector. So if I'm talking about vector AB or vector V, they call it here, if I want to find the unit vector, I just take that vector and divide it by its magnitude. And you can see that's what I've done here. So I took each component, divided by the magnitude of that vector. Now I've got a resulting vector that has a length of 1. Okay, so knowing that has a length of 1, I need the length of that vector to be the square root of 5. So now all I'm going to do is I'm going to multiply by that scalar value, square root of 5, and that's going to give me a vector that now points in the same direction as AB, but has a length of the square root of 5. So I essentially reduced it down to a vector that has a length of 1, and then just multiplied by whatever scalar I needed to get the length that I need. Okay, so let me show you a couple more problems here that I want you to try. And it says, find unit vectors that satisfy the stated conditions. So we've got some given vectors here. We have negative I plus 4j. We have 6i minus 4j plus 2k. And then we also have a vector that goes from A to B. So for these three, they're asking you to find unit vectors that are described. So I want you to pause the video, and I want you to try to quickly solve those out. And then when you've got your solutions, you can unpause the video and check your answers. Okay, so here's what you should have come up with. It says the same direction as negative I plus 4j. So all I really need to do here is figure out the magnitude, which was square root of 17. And now just divide both components by that square root of 17, and that's going to give me my unit vector. So again, remember, when you see this notation, when I divide a vector by its magnitude, I am finding the unit vector that points in the direction of that vector. Okay, so we also have for B, oppositely directed to 6i minus 4j plus 2k. So what I did here was, again, remember we need a unit vector. So I got the length of vector V. I just called it vector V. And I said that's 2 root 14. And now this is where I got my unit vector. And then from there, if I need it oppositely directed, all I've got to do is just multiply by a negative. And if you notice with my unit vector, I've already taken that negative into account. So you can see that originally this was 6i, I multiplied by negative 1. This was negative 4j, now I've got a positive here. This was positive 2k, now I've got a negative. So I already took the direction into account when I created that unit vector, and then the next step was just simplifying. So as far as simplifying goes, the simplifying is not that important from the standpoint of, getting all your square roots simplified as much as they can be and that kind of stuff. The main thing I will tell you is on a lot of the questions I'm going to ask you, you're going to have to do multiple choice, and your answers are typically going to be in a simplified form. So you're probably best off just getting in the habit of simplifying. Same thing with the homework. When you check your answers with the homework key, typically they're going to be in a simplified form. So you probably ought to just get in the habit of simplifying, even though if it were a free response on a test, I won't require you to simplify them down all the way. All right, and then the third question here, they want us to have the same direction as the vector from the point A to B. So this is similar to that problem we did a few minutes ago. So I found the vector AB. I just did x2 minus x1, y2 minus y1, and z2 minus z1. But I got this vector AB here. And now I just need to find the unit vector. So I found the length of it. It was square root of 18 or 3 root 2, and then just divided each component by the magnitude. Okay, so again, very, very simple stuff. When you do the assignment for this section, I know the questions are easy, these need to be things that you can do without even having to think about it, because we're going to be working with derivatives and integrals involving vectors, and you can't be getting stuck on the basic vector operations. That needs to be a part that is like 2 plus 2 to you. You don't even need to think about it. So that's why we're spending a whole day on this, so that you can really get this stuff fresh in your mind, and then just drill a little bit of practice with it, so that this is not something that we have to stop and think about every time we need to do it. Okay, so let's take a look at this last problem. And on this last problem, it says sketch the vector u plus v plus w and express it in component form. Okay, so really everything is shown in this graph. So what I want you to do is actually write out what are the vectors u, v, and w, and then find u plus v plus w. If you want to sketch what that vector would look like, you can sketch the vector, but the most important part here is to actually find the individual vectors and then find u plus v plus w. So pause the video, take a minute and solve that, and then when you're done, unpause it and I'll show you the solution. Okay, so here's what you should have come up with. You can see that for the vector u, I've got to take a look at these components here. You can see I went 5 to the right and 5 down to get to that endpoint. And then for the vector v, you can see I went up 2 units, but I also went to the left 10 units. And for the vector w, I went to the right 3 and up 8. And now to get the overall sum of those 3 vectors, you're just going to add component by component. Add all your I components together, add all your j components together, and that's your resulting vector. And you can see I kind of crudely sketched it there, but that's the idea. Whatever your starting point was, line up your vectors head to tail, and it goes from your starting point to your final point, and that will be the resulting vector. Okay, so as far as homework goes, let me show you on the next page of this. So I gave you a bunch of problems that are out of the book. You hopefully will find that relatively easy. We're going to get into dot product and cross product next time, or next time we do new material. And that's where the difficulty level on this is going to ramp up dramatically very, very quickly. So take the chance that you have to focus on this easy stuff, and don't just rush through the assignment and get it done as fast as you can. Make sure you're paying close attention to your notation. Pay close attention to, the alternate notations that you can use, how to read them, how to write them. Pay close attention to the notations you have for unit vectors, all those basic operations. So that way, when we're doing, a dot product and especially a cross product, with a cross product, things are going to get a lot messier. You don't want to be getting stuck on these easy parts with the I, the J, and the K. Okay, so addition to the questions in the book, what I've also included here is I want you to do a little bit of graphing practice. So I do have some isometric dot paper that I attached into the lesson video, and I guess I put it on the assignment as well. So if you need isometric dot paper to graph these things out, it's sort of a little bit of a tool you can use to make it easier to graph these. Get a piece of that isometric dot paper and graph it that way. If you want to freehand it, you can do it that way as well. In the end, in this class, we're not going to use isometric dot paper all the time. We're just going to use, probably just our lined white paper and just do a sketch of our graphs. So if you want to just start now and do it freehand, you can do that. But if you feel like you need the isometric dot paper to start with, do it that way. But in the end here, what I want you to do is graph these figures, and I want you to label or find the components of all of the vectors for these. So it's some different shapes. So it's some 3D graphing practice. It's also vector graphing practice. It's also practice with a little bit of stuff like, for example, when you find the components for your regular pentagon, you're going to have to do a little bit of geometry to figure out what those components are. So there's going to be some review material mixed into this as well. So it's what's in the book and also what's on this practice sheet. You are going to have the entire time for the second day of this material. So in class, when we discuss this, we'll go through this. You're still going to have a quiz that day, but then the following day is just going to be a work day. And I'm probably going to break you into groups, and let you guys talk about things. You can talk about your graphs and that kind of stuff. So if you have any questions between now and class, feel free to email me and let me know. Otherwise, we will talk about this in class, and then you can get started on your assignment.